Ashton Miller, Oxnard College Physics here, and we are now prepared to move onward with some fascinating physics facts. All right, so what we want to start delving into now is, well, what produces acceleration in the first place? We've looked at motion of an object. We've looked at acceleration and how it's characterizing a change in velocity with respect to time, and how displacement occurs as an object's moving, and the correlation between them all. So what we want to get at is, well, what makes something accelerate in the first place, right? What makes it change its motion? That's what it really comes down to. We want an object to change its state. What do we need to do? What do we mean by its state? Well, its state is what it's doing. Change what it's doing. Make it do something else. Make an object that's initially at rest move. Or an object that's moving, move in a different direction or move at a different rate. How do we change the motion of an object? Well, that's what acceleration is all about, right? Characterizing that change in motion, change in velocity with respect to time. So this is what we want to focus on now. And, well, let's just take a look at this. I can take an object and say, yeah, I throw it at some angle with some initial velocity, and it becomes a projectile. Fantastic. We looked at projectile motion, great. But what about the before, right? What about me giving it its initial velocity as it becomes a projectile? What did I do? You said, well, you threw it. And yeah, that's right, I did. But let's look at that a little bit closer. Let me take this object like this, and what I'm doing right now is holding it at rest. Object's at rest, and then what do? Well, over some distance that occurs over some time, I'm taking it from rest to some other velocity. And then I release it with that particular velocity that has a magnitude and a direction. And at that time, it's then a projectile and does what it's going to do. So I take it, and I change its state from motionless to the instant when it leaves my hand, having some initial velocity. So it's all about the what happens before, right? I take it here and I act on it. What am I doing? I can say I'm pushing it. And while I'm pushing it, I'm changing its state. I am accelerating it. And that's it. So this is what we want to start looking at. What produces acceleration in the first place? And, well, lucky for us, there was this pretty smart fellow named Isaac Newton that is kind of the grandfather of physics in a sense. He produced calculus to better understand the world around him, really to correlate his ideas about physics and such things. And he happened to produce a few laws called Newton's laws of motion, 3 of them that really allow us to examine what we need in order to produce a change in an object's motion. So we'll look at Newton's laws of motion, and then we'll kind of make some correlations with it. So first off, let us define something. We're going to define what is called force. We're going to say that force ultimately constitutes a push or a pull acting on an object. So I take this object and I push it, or I take some other object and I pull it. We can say in that I'm exerting a force on that object. So a force is characterized by C-H-A-R-A-C-T-E-R-I-Z-E-D, characterized by a push or pull being exerted on an object. And well, what we want to do is first discuss different types of forces And we'll take a look at Newton's law. Yeah, let's do this. Two categories of forces. One is a contact force. A contact force is just what it sounds like. A force that is exerted on an object via physical contact, via some physical contact. So I push on something, I'm contacting it. I'm actually physically in contact with this object, and I push or pull on it, I exert a force on it, we call that a contact force. Anytime we have something touching an object, there's some sort of force that is exerting on that object. We call that a contact force. Now, it doesn't just have to be me contacting something. I can take this ruler and have this ruler exert a contact force on this ball and do stuff. So there's different ways of exerting contact forces that we'll get into, but that's kind of the typical, right? Well, there's another category of force. You may say, well, nothing's touching something. How do we get a force? And well, that's a good question, but there's a good answer too. We have what is known as field force. Field force exerts a force on an object with no direct contact. So what's an example of this? One example of this would be something like, well, what happens if I let go of this pin, right? If I let go of it, it's like something's pulling it down to the ground. I didn't see anything touching it, but something's like pulling it down, changing its state, exerting a force on it. What do we say that something is? We say it's the gravitational field force. We've also got some other field forces, magnetic field forces, electric field forces. There's other types of fields, but field theory is ultimately a way to describe force that is exerted on an object at a distance that requires no direct contact between the object and whatever is exerting that field force. So those are the two type of categories, and when we start analyzing systems, this is what we're always going to ask ourselves. Is there any contact force exerted on the object in question, and is there any field force exerted on the object in question? And generally, for the field force, the answer is going to be, yeah, if we're on Earth, there is a gravitational field force acting on it. And generally, we're going to stick with objects that are on Earth. So that's going to be something that's in the mix quite a bit. This one just really depends. What else is touching the object? So this is kind of what forces are. What we really want to know, though, is what does a force do? What are Newton's laws of motion that have to do with force? So let us take a look at that. Newton's laws of motion. So, law number one. Something you've probably heard before. It's sometimes referred to as the law of inertia. It says that an object that is in motion tends to stay in motion, an object that is at rest tends to stay at rest, and then there's some other contingencies there. Object at rest stays at rest, object in motion stays at motion. That's usually what you hear. It's a little bit more elaborate than that, so let's go ahead and write this down. So Newton's first law of motion is an object that is at rest will remain at rest. And an object that is in motion will retain that motion. unless it is acted upon by a non-zero net force. Non-zero net force. So net force, net means sum of, mathematical sum, SUM. If we add all the forces acting on an object and the net result is 0, then the object does not change its state. If it's initially at rest, it remains at rest. If it's initially having some motion, it continues to have that same motion. Constant velocity. For all time until there is a non-zero net force acting on it. So this is basically a nice statement that says what changes the state of an object? A non-zero net force does. That's it. All right, so we'll come back and utilize this. That's something very nice that we have regarding forces. A statement that helps us understand what happens, or what doesn't happen for that matter. The second law. Ooh, this one's going to be something we use all the time because it's a nice mathematical statement. It says, this. That's Newton's second law. What does that mean? Well, this is sigma. And sigma mathematically means take the sum. SUM of. Sum of. Not like a few of, but sum. Add them all up. This says the sum of all forces acting. So put that. Sigma F hat is the sum of all force, and notice we got a little hat here, vector, right? The sum of all force vectors acting. So this is explicitly telling us force is a vector quantity. Yeah, it's a vector. I can push on something that way or that way or that way. There's a directionality associated with a given force. So there we go. It has to be a vector quantity. So the sum of all forces acting. Then we've got equal sign and an m times a hat. Well, the ultimate way to read this statement is the sum of all forces acting produces the acceleration of the mass on which those forces act. So let me just write that down. Sigma F is the sum of all force vectors acting on an object of mass m. A hat is the acceleration vector produced by the net force. So again, we don't want to say a net force is a mass times an acceleration. Sometimes this is misread, misconstrued with this equal sign. It's a net force produces the acceleration of the mass on which it acts. So overall, that's important to write out. So let me just write that. Second law. Net force acting produces the acceleration of the mass. we go. That's how we say that expression right there. Net force acting produces the acceleration of the mass on which it acts. There we go. So, what do we want to get out of this? Well, get that there's a nice mathematical representation of what produces an acceleration. A net force acting on a mass produces the mass's acceleration. So there's some other things with respect to this. Mass, we haven't really talked about it that much up until now because we haven't needed it. Once we start examining forces, we do need the concept of mass, which we talked about a little bit in the very beginning, mass being an inherent property of an object or collection of, I shouldn't say or, it is ultimately the collection of all the particles, all the protons, electrons, and neutrons of which an object is composed. It's how much of the object is there. We correlate it a lot with weight, but weight and mass are really two different things. Weight is the interaction of mass with a gravitational field. Mass is inherent in the property, is an inherent property of the object. Where the object is the same amount of mass. It's not true with the weight of an object. Go far out into space or go to the moon or Mars, you got different weights for a given mass. Anyways, that is something that is a constant proportionality, really, between the force vector, or net force vector, and the acceleration. So we think about this. Is it harder to set an object into motion that has a large mass or a small mass? And the obvious answer is, well, it's easier to ultimately change the state of an object that has a relatively small mass. You think about taking this ball and bringing it from rest to some velocity of, whatever, 15 meters per second, and then trying to take something that's substantially more massive and doing the same thing. No, I'm not going to throw it. It's harder to make this one go just as fast as I made that little ball go, because there's more mass that I've got to exert that force on in order to produce that same acceleration. Anyways, mass has a big part to play. It's definitely more difficult to change the state of a more massive object. And that's what acceleration is all about, right? Changing the state of an object. And the force is what produces it. All right, so let us continue on with this, shall we? We've got some other things that we can extract out of this particular expression there. How about the units? SI units of force. Sometimes we'll just do this. This means the units of net force, well, they have to be equal to the units of mass times acceleration. Well, the units of mass times acceleration is kilograms for mass, right? And then acceleration is meters per second squared. Units of mass, units of acceleration, SI units. So what we would really say is this is kilogram meters per second squared. That's how we quantify force. It's very compound, right? Very compound, but it has units of mass times acceleration. We go ahead and call this something else. We have that 1 kilogram meter per second squared is equal to 1 Newton. That we just used capital N to define the unitization. So in SI units, the Newton is the unit of force. In American standard units, or US customary units, we use pounds. Pounds is a unit of force. But SI units, we use newtons. And we'll get into conversion factors later on. This is how we're going to quantify forces in terms of their magnitude. How many newtons of force did you exert? So let's take a little look at something here. just to get something down in terms of mass and acceleration and net force. So I'm going to take some object here. I've got this little crate. It's really not that massive. It's empty. Put it on this table. Let me move this table up a little bit so you can kind of see what's going on. And what's on the table right here, you got to kind of take my word for that. And I've got this little scale here. Well, this scale is measuring the number of newtons that is exerted on it, or that it exerts on something for that matter. So there's a little hook right here. I can pull this hook down and notice the needle starts to deflect. Right now it says 2. Well, that's 2 newtons of force that I'm pulling down with. Now it's 4 newtons of force. Now it's 8 newtons. Now it's 10. Oh my gosh, there's 20 newtons of force. Can you see how hard I'm pulling? No, probably not, right? But nonetheless, I am pulling down harder and harder and harder, and not that much now. What I want to do is actually pull on this. So I've got a little string attached here, and what I could do is attach this little scale here, and right now it reads approximately 0, right? But what happens if I start pulling on it? Well, by pulling on it, it's not moving yet, but what we want to do is just kind of have it slide at a nice even rate here. In order to move this, I have to exert somewhere between 5 and 6 newtons of force to move it at a constant rate. Well, what happens if I make this more massive? How am I going to make it more massive? So let me take something that has, well, probably twice the mass of this. This isn't super heavy, but it's heavy enough. We'll stick it up there. We'll do the same thing. What do you think is going to happen when I pull on it? Well, the same thing's going to happen. This is going to reach some number of newtons, but the amount of force that's going to be required to actually set this into motion is greater than 6 newtons. Let me keep pulling on it. Oh my gosh, now it's 8, 10, it's still not moving. 12. Oh, it looks like about 13 newtons of force is needed to move this at a constant rate. So 13 newtons of force pointed that way. The point here is that it was harder to set the more massive object into motion, or change the state of the more massive object, relative to when it was less massive. And that is that M there, constant of proportionality. So, that's just something that we've got going. All right, so there's Newton's second law, and we'll be investigating this a whole bunch throughout this course. Well, let's go ahead and move on to third law. Which is often referred to as the action or reaction law, and you've probably heard some variation of it. For every action, there's an equal and opposite reaction. That's a typical statement that you hear. We'll be, again, a little bit more picky in how we word it out. So let us take the third law and say, when 2 or more particles, objects, interact, when 2 or more particles interact, comma, the forces that they exert on one another are equal in magnitude and opposite in direction. Opposite in direction. So what does this really say? What does interact mean? Interact means ultimately exert force. If I push on something, just as well, it's pushing back on me by contact, right? If 2 objects are contacting each other, they're exerting forces on one another. And if the force of one varies, well, the force of the other does too. When objects are in contact, they exert equal and opposite forces. It follows just as well with field forces as well. A little bit harder to see, but really it's just the notion of 2 objects interact, 2 or more objects interact, They exert equal forces in opposite direction. I can take myself here and I can push on this. I can push on it light, I can feel the pressure in my hand. I can push on it harder, feel the pressure on my hand getting, well, increasing. Pressure is really the force distributed over some area. We will get into that later too. But the harder I push on something, the more pressure I feel itself. That's because that something just as well is pushing back on me. You say, well, how does a wall push on you? It's due to me contacting it, but in itself exerts an equal and opposite force as I contact it. Anybody ever hit something? Not a person, just something like, I don't know, a bucket? Kick the bucket? No, we won't kick the bucket. We'll kick the bucket. Take a bucket, right? Whew. What happens if you hit it? Oh, that hurt my hand. Shoot. Hurt the bucket too? Well, not really. Seems to be okay. I definitely exerted a force on the bucket, but while I was exerting a force on the bucket, it exerted a force on me too. It changed the motion of my hand. My hand was moving in with a certain acceleration, and when I started contacting the bucket, it changed the motion of my hand. And it hurt a little bit because, well, it exerted a force back on me. So, that's pretty much what we've got going on regarding what forces do and don't do. We'll come back to this third law in different applications to really understand different systems. But really, it's this second law that we're going to focus much of our attention on, utilizing it. Net force produces the acceleration of the mass. So, yeah, let's just take it there for right now. Take a little break. We do a little problem, elementary, and then we can discuss other systems. Sound good? Of course it does. All right. See you in a bit.